And I think we are ready to go. And it's open source organ construction. I'm really excited about it. All things that you can build yourself is being open sourced, and prototypers are conquering everything. And I'm very glad Benjamin Wandt is here to talk about organ construction with 3D printers and electric tinkering. He brought along Yannick Bayerstadt, is assisting with the mechatronic parts and communication technology parts. And I'm very excited what the update is on this topic. Thank you very much.
Ja, guten Tag.
Yeah, hello. Thank you for coming on the last day that you may have found your way here. Most people probably think an organ looks like this, but in hackerspaces, I wouldn't recommend building a big one, more like this one. Maybe you could wheels on it. Maybe I should say that I'm not planning to build a big organ, but if a hackerspace wants to build one, I can really support you. I'd really like to do that. And maybe trying to define what an organ really is. The data has to go in, compressed air has to go somewhere, and data and air have to convert it to structured air, and that goes into the pipes and sound will come out. There are some gray areas maybe. Is an harmonium, is that an organ? But I don't have to answer that. It's just a gray area. And you could also say that you can make a wider definition of an organ, and that's perhaps something like a machine that makes continuous sounds that are not percussive sounds. And then maybe a Hammond organ is also an organ then, in that definition. I wouldn't really require a manual or a keyboard, because little automated things that also produce tones like that may also be organs. And here are some pipes. Pictures of some pipes, typical organ pipes. Until number 14, they are lip pipes. They work like a recorder, and there are reed pipes. They work more like a clarinet. And there are some miscellaneous pipes, other pipes who likes experimental things, they can search for vox maris. That's another pipe type with very high pressures and very high volumes. Except some very few exceptions. A wind instrument always needs a generator and a resonator, and the resonator is the pipe, and the generator is what makes it resonate, what makes it oscillate. With a brass instrument, you use the lips, and maybe there's a reed in some instruments, and some resonators and generators have different sounds, and that's why there are different types of organ pipes. So they all sound a little bit different. My own designs, I always thought that you put in a pipe, and you are restricted to cylindrical pipes then. All the pipes are parametric in FreeCAD or OpenSCAD, and you have to put in the value and for diameters and such into the file, and then export as STL, and then you can put it into a 3D printer. In FreeCAD, it's a spreadsheet. There's a spreadsheet for entering variables, and there's one area to enter your values. And you see here some schematics of a metal organ pipe on the left and a recorder, and some of the things that I do on the right. There are many reasons for design decisions, for details, for organ pipes. They're all quite different, but roughly 99% of the reasons why they look the way they do roughly are questions of practicability of building the things. These metal organ pipes are from sheet metal soldered together, and that's why they have thin walls everywhere, and that's why there's air in the bottom here, because it's the easiest way to build it. On the other hand, a recorder, you just drill a hole into a piece of wood, and then you make the lip there, and then you put in the block there, and that's why there's the big black block there. That's caused by the way it is built. And if you use a 3D printer, there are a completely different set of rules. I push in a block of wood isn't relevant here, but what's really interesting here is that on the bottom it is hollow below the lip, and I didn't think of that immediately. But at first I printed pipes like recorders, and yes, that works. But the generator doesn't have to be at the end of the pipe. So if you look at a transverse flute, and the generator isn't at the end of the pipe, and I really didn't look at it, but Helmholtz said the generators should be at the 7/8 point. So if you don't know where to start, maybe that's a good starting point at 7/8 of the length. I have made several flue pipes from the Thingiverse, and I wasn't really excited by any of them. These organ pipe shape depends on the way it is machined after building with machining tools, and with organ pipes, with metal pipes, that works very well, and it doesn't work very well with plastic from a 3D printer. And you don't really have to imitate the shape of a normal organ pipe if you really want to have something like that. And I wanted to say something about the design programs. I started working with FreeCAD and then went over to OpenSCAD, and they are very different approaches. But in practical handling, I'd say if you need to do something very quickly, you just use FreeCAD, and you can just roughly make something. And if you think it's going to be a real big project and it has to scale, then maybe it's a good idea to code it again in SCAD, because then it can really be versioned and it doesn't crash quite as often. One of the reasons why it's such a problem with FreeCAD is if you enter the parameters in the spreadsheet, then after every entry, the model will be recalculated, and maybe there are mathematically impossible models, and then it'll just hang and crash. You can try to enter the parameters in the correct order, but it's quite unnerving and takes a long time, and it's annoying. It's no fun at all. And a problem with OpenSCAD that I found is that the files can only work with specific versions, and someone gives me an OpenSCAD file, and then then it doesn't work, and you have to talk about program versions, and it can be fixed often, but it's still very not quite ready yet. Maybe they really have to think about what they really want to achieve. So what about plastic? Don't they break quickly? Well, organ builders really claim that their organs last for centuries, and that's a big thing to claim, because they are moving parts, and an organ always comes along with a maintenance, doesn't come along with a maintenance contract, and they sometimes break, and then they are half broken or something. And I would suggest that be realistic about that and make some estimates how long the parts will last, and you could perhaps consider that one version lasts for 100 years and one lasts for 50 years, but only costs 20%, and you can weigh your priorities. And I wouldn't really print something that should last from PLA. That's nonsense, but you can also print nylon, and you can also come and look at this. I have something printed from nylon, and that's almost serious, really. Okay.
On
the Easter egg hack, I had just finished a design with a 45-degree lip, and I couldn't play it because there was a problem with a 3D printer on Easter egg, but it's done now, and I can demonstrate it now. That's what it looks like. I did that because I always printed them at 45 degrees angle, and all the flue pipes had problems with the support materials. And if I make the labium at 45 degrees, then I can print them upright, and it'll stick to the building plate, and there are really no problems with that. It makes sounds just like other flue pipes, and that's all fine there. I couldn't find any difference really if you build it 45 degrees or straight up. And in spring I had done experiments with the reed generator, but I didn't follow up on that. And I really wanted to mention it because I still have the project to build a prototype with real dynamics, like with a piano. And so keyboard dynamics, I mean, if you touch more, if you hit it harder, then it's going to be louder, and if you maybe something like this. So this is a piano, and for all non-musicians, perhaps. And if you make the same thing with a Hammond organ, then yes, it's always exactly the same volume.
Dann würde ich das Spektrogramm einführen. Das
Then I would introduce the spectrogram, and I did that rather lazily on the Easter egg, rather sloppily. And the lower bars are always what you hear consciously, and everything above that are harmonics. And whistling has hardly any harmonics, but singing does. And can you see the stripes there? And I think that's really a very interesting toy if you build instruments as a hobby, musical instruments as a hobby, and it's a very nice toy. And then you really have a visual feedback for what you are doing there. And where's the pipe here? Okay, here's the pipe. So this is a pipe that I had a moment ago. Okay. One problem with the dynamics is there are several problems, but one of the problems is that the flue pipes, the pitch changes when you blow hard. And they will overblow. If you blow harder, they overblow and go into the upper octave. So just change the airflow is quite limited. And I have this. I have an inverted reed generator here, and you can see in the spectrum that it gets more overtones, more harmonics, but it doesn't. So you can see it gets more harmonics, but the pitch doesn't change, and they don't overblow. So if you do something with dynamics, then that works. So it's a potential candidate for a high-pressure register, a high-pressure stop. And most flue pipes that I have made, they work with between 40 and 50 millimeters of water column, and the reed pipes more or less at 100. So talking about millimeters of water column, there's this toy here. This is an experiment making a very simple intonation work. And building an organ. They have different jobs. Some people build the pipes, some people tune the pipes. And tuning the pipes isn't done during the concert or in the organ, but in the workshop. And you can try them. Here you can. Why don't you just blow in with your mouth? Because they contain lead. But I can't open the bottle. Right.
Sonst müssen wir Wasser nehmen.
Otherwise, we'll have to take water.
That's not how to, because organ pipes are specified for a certain air pressure, and this specified air pressure isn't working when you blow in with your mouth. The most of the time where there were where we built organs, people couldn't read and write, but there's no problem with this. So what I'm doing with this is I'm filling water inside this columns. Oh, it's been a bit much water. Where is my cup? It's a little bit of experimental setup. Could you actually see this? It's a bit shitty that this colored water.
Gut.
Okay.
Also zumindest hat es jetzt eine gescheite Menge.
At least it's now a good amount of water.
Ja, so halbwegs, ne?
Can you see it on the video? Yes, it seems so. Here.
Ah,
Jetzt haben wir auf.
du hast es auf. Okay, dann machen wir das
Okay,
jetzt mit weiß.
you have it open.
Wirklich sehen, was passiert. Das ist sonst,
You have it white because then you can actually see it.
So, das kommt also wieder raus.
So that's going to be out of the setup.
So, also
So.
auch 3D gedruckt.
This is also print from a 3D printer.
So, noch ein bisschen.
So.
Also bis zur Hälfte würde ich
Just a little bit. I'd suggest to fill it unto the half.
So? So
So.
war das gemeint.
So that's been meant.
So, und dieses
And this
Ding.
thing here,
Ja, scheiße. Okay, ich halte es auch einfach mal hoch.
I'll hold it up so that you can see it.
Nochmal in die Kamera.
And then I hold it in the camera so you.
Das war so mein erster Versuch. eine
This was
Nachtigall
my
zu bekommen.
first
Eine
try
Nachtigall ist
to
ein
make a.
Wasser drin.
Nightingale.
Aber
I put inside there real water.
Und was wir jetzt hier experimentell versuchen
And
rauszukriegen,
what we are
ist,
trying to find out experimentally is,
die Nachtigall festhalten, nicht, dass
Yannick,
wir
please hold the Nightingale
das ist eine große Sauerei veranstalte.
so that it doesn't turn over and I make a lot of mess. So I'm blowing inside
Und jetzt hören wir noch nichts.
the chamber and we don't hear anything by
Das
now.
hat Tasten, also wie ein
So
Klavier,
there are keys like a clavier.
Jetzt kommen langsam Töne.
And now there are coming tones.
Definiert das Ding, weil das ist das, was es
And the question is at which pressure it started trilling,
Okay.
because that's what it should do.
Mal eine andere.
So we take a different one, because it sounded shitty.
Warum geht es nicht?
Why isn't it working?
Ist das für ein Themaarsch?
Is the valve broken? That's the thing when you build something on your own.
Okay.
Okay.
Oh, sie hat noch nicht genug Wasser.
Oh, there's not enough water
Man
inside.
kann es leider von außen nicht so gut sehen. wie viel
One
Wasser
can't
drin
see it. One can't see it from the outside. How much water there is in there?
Mal probieren.
Let's try it again.
Genau.
Yeah, right.
Also jetzt kommt erstmal überhaupt ein Ton.
So now there's tone,
Und an der Differenz
and
von diesen beiden
on the difference of the both water columns, you can see what pressure there is.
Mal probieren.
Try it again.
Genau, das meine ich mit
Okay,
Derivieren.
this is what I meant with the threading.
Genau, und so kann man also
Right,
irgendwelche
and this is
3D-Drucken
how
pfeifen, ja,
you
das
can
da einfach anschließen und dann
attach 3D printed organ pipes to this and test them.
ja.
That's the goal of the exercise here.
Und dann, wie gesagt, ich wollte ja was mit
Okay, as I said, I wanted to do something with dynamic, and
da könnte man jetzt
one could now
Input-Vektoren nehmen.
take different input vectors for the dynamic,
Wenn man die Geschwindigkeit misst,
and if you measure the velocity, you turn
bei einem elektrischen
pull.
Klavier. Da wird meistens die Geschwindigkeit gemessen und
You can
daraus
do it like a
gibt es
digital piano. and then convert that to the volume, to the amplitude. And then you can also measure how strong you press the key down, with what force.
And that's really something you use for in real organs. And I wouldn't call it dynamic, but expressive play, because with the following reason, with half-pressed keys, no one can play. That means if you take the height of the key as an input vector, you wouldn't influence the loudness of the key, but the start of the swinging of the pipe. And this is, of course, interesting, but it's not the dynamic as I thought it should be. What you also could take is the pressure on the key, and I have a pressure sensor here, which I take as a sensor for this. And what you see is just read in with an Arduino. This here is what I think it should be. And you can come forward to me after the talk if you want to see it. Now you would need not just a sensor, but also an actuator, and not just one, but many of them. These are the valves as they are inside the intonation needle, and there's a block and a spring inside. I decided for this form because I could 3D printed it very easily. I don't know. I wanted to do this, and Yannick wanted to work with actuators for a long time, and the state was for a long time on maybe, but as he's seen this, it was going forward.
So we swap seats. All right. Okay, the problem was we need some sort of valves that are cheap, because we need a lot of them, and otherwise it's going to get expensive very quickly, and the valves have to be driven somehow. And I started with something like a cone, pushing a cone into another cone, and something like that. And then Benjamin came up with something for the keys there, and that was my starting point. And for driving it, we need some positioning drive, and it has to know the position, or I need to know the position when I want to drive it. And so I can do it by knowing the position from the driving itself. Some people will know what I'm talking about, but I'll explain it in more detail. Or I'll have a position encoder, and they are linear or for rotational movements. But then I need a control feedback loop, and I have one value that I measure, and I know where I want to go, and I have to put the control such that the difference goes to 0. And for this feedback control loop, I need real-time controlling features. And if I do that with one microcontroller with maybe 25 drives there, that's rather challenging, perhaps, and needs a lot of computational power, and the hardware is quite expensive then. So what possibilities do I have there? There's this kind of drives, that the actuators that Benjamin showed us from Otto Heuss, making parts for organs and selling them. And these actuators can also regulate and change the position. I want to have it 100% open or 50% open, but they are quite expensive. And then there are two coils working against each other, and it maybe uses a lot of power. I had tried to do that with some solenoid valves, So what a loudspeaker makes, what a loudspeaker uses, but that's quite expensive. It doesn't really work very well. And there are these RC model servos. They are rather cheap, but when they are cheap, then they are expensive. No, sorry. Then if they're cheap, they are loud and also quite slow. But controlling them is easy because the position control mechanism is inside the servo, and there's something that measures the position, and it's all automatic. And the professional version is this is a servo actor, what's used in industry or in the powered steering in a car. There's a motor and a position encoder. This is only the encoder. You see, and with good quality that's quite big and expensive. So yeah. And many of you probably know from 3D printers know stepping motors. And by controlling them, it is known where it is, at which position it is, because for one control step, there's a certain rotation. Standard stepping motors probably usually have 200 steps per revolution, so 1.8 degrees. Then you can do some tricks to increase resolution, but normally you know the position. So what are the advantages and disadvantages of stepping motors? The advantage is you know the position unless you put too much force on it, too much torque on it, then it may skip a step, and then you have a problem. And if someone with a 3D printer knows the problem, maybe one layer is shifted then. But position control is relatively easy because the controlling is you just have to count the steps in each direction and just calculate plus and minus and addition, subtraction, and you know where it is. And the position resolution is quite good, it's quite high. It's precise enough for what we need to do. The first estimate is that perhaps you need about 20 steps, 20 volume steps to use it, to make a useful discrimination, so that you don't really hear steps in the volume of the instrument. So yes, that was my estimation, about 20 perhaps. And the disadvantage is that normally if you have small stepping motors that are cheap, then they have a very low force and low torque. And the valve design that we currently plan to build, that's not a problem. I'll show you in a moment. And they are sometimes loud, and it depends on the way you control them. For example, in a 3D printer, maybe you know that they make funny noises if they drive back and forth. And there are several special driver chips that can do that better and are almost noiseless, very quiet. And then about valves, it's nice if you just have the key at the bottom and just have to push it down. And then why does it have to be a linear movement? You can also do it in a different way.
Okay, so I can also simply build in a way that the motor is put directly to the valve, because then you put this, but this is not good, because if you need to put the spindle there, and then you have this nut which is going forward and backwards, which is pretty expensive in terms of parts and building. But you also could put their stepper motor to attach one stepper motor to one of these tubes, which then turns around the tube about 90 degrees, and you can think about how far you might go, but you need to take care of that you can switch fast enough, because the motor needs some time. So for the controlling, that's pretty straightforward. You use a microcontroller, which is a processor for which are processor for multiple in and outputs. Per stepper motor, you need 3 in and outputs, because the most easy interface for a stepper motor, you have a step direction interface. So you have one pin, you go from 0 to 1, and each time you change the amplitude, you go forward or backward, and then you can say that it should go one step. This you're doing over the direction pin. Also, you would need an end stop switch, so that you know that you're being on your final position or position 0. And the valve is completely open or closed. So you need 4 contacts, and there are controllers which can handle this. I have a TIVA board which has about 100 GPIOs, which you can use. So this is a good thing you can use for control organ pipes. You can imagine one octave has 12 tones, and if you want to have two tones, you have 24. If you would have one tone for the third, 25, and therefore you could use with my device control with my device about 30 pipes. So now we have a valve, we have a controller, we have a driver for the controller, we can attach it to the microcontroller, and what we are still missing is the data from the input device. It might be a keyboard with force sensors, or you also could use punch cards from turning layers. You would get rid of one digital layer by using this mechanical way to control it. And it would be a good idea to use something like this for a generic storage way for what someone put into a keyboard. And then bring it to a hardware device. So our current idea is to use MIDI, which is a serial protocol, over the UART port, going to the different devices. If you don't know what this meaning, it's universal asynchronous receive and transmit, also universelles asynchronisches Empfangen und Senden. Das Asynchrone bedeutet, das ist halt so auf dem Mikrocontroller programmiert, das ist nicht so wichtig, aber es ist halt nicht ganz so einfach zu benutzen. Ein sehr einfaches, also MIDI kann noch viel mehr.
First byte says what it is, what needs to be done, and then it's one for node on and node off, and there's various different things. And the second is the pitch of the tone of the note, and the third is velocity. That's usually used for loudness, for the amplitude. So what really should be better in the future is a protocol called Open Sound Control. It's called OSC. That is based on network-based. You have Ethernet cables and switches, and they talk to each other using UDP packets. And this, it's possible to, if you don't build just a small device but have many pipes, then you need more controllers on the output side, because sometimes you don't have enough pins on the controller, and maybe you really want to have different input devices. And on an Ethernet switch, that's very easy to connect them rather than with MIDI cables and loop through and things like that. And it has some more features. For example, to change the volume on a node that's already playing, and it's quite easy to build a network like that, and you could think how to configure that, but you'll have one unit with one organ voice, and it says you have C3 up to C5, and for example, then it could react to the network inputs and not to any others. Okay, now we perhaps have a small demo. If it works, perhaps, hopefully. It's all just during the last days we cobbled that together, and I would have liked that it sounds like something. Yeah, I would try this with our motor to do tones, but I left the air pump back at home, so you can just see the motors. Can you see this? Yes, maybe. No, put it a bit more over to me. You might see now eventually a big heap of cables, like what, as it is today, you use a breadboard and put in a lot of stuff there, but later on we wouldn't use different boards with chips on it, but in a way cheaper. But as said, the problem was to print out all the valves, but if we would press here this key, you would see that the motors would turn around, and in theory it would play a free software song, but not here. Maybe in the other demo. I could turn on the free software song.
Also man sieht, die sind schon ziemlich fix.
One sees they are pretty fast if you just go to 90 degrees. So that's why we choose them. And if someone is interested, you can come and ask me. And this is what in general should be enough to play fast with an organ. Organ music is in general pretty slow. What? Some of it is slow, but the question is how fast you can play the tones. It's depending on how fast the pipes are going to respond, and that's more like the problem. Now from here I don't hear anything. I had my problems with stepper motors. They might be loud, but I was wrong. The other one I did with the coil, I pushed it on a wooden part, and you can't hear it with a wooden part. So they are pretty quiet. So we came to our end, and everything else in a Q&A for details or other questions or ideas what we can improve. Thank you.
Ja, herzlichen Dank, Benjamin. Herzlichen Dank, Yannick. Ihr habt's gehört.
Vielen Dank, Yannick. There's a call for the mic. There's one in mic 1. So, hello. What's speaking against the mechanical control, like a mechanical swing, and then you put there an electromagnet? Yeah, that works if all you want is turning on and off, and I really want to make a dynamic organ. But with dynamical pipe, with reed pipes, this wouldn't. Flue pipes. Flue pipes, yeah. Okay. So I have to go back a little more. There are lots of pianists. You couldn't play a clavichord, and of course there are people that can play the clavichord, and of course you can play on that. And some time ago I started playing clavichord, and the first 2 months it sounded horrible. And you really have to, if you really have such a sensitive actuator which changes the pitch, it doesn't mean you can't use it. It's something that you have to learn, or what the musicians have to learn to that the pressure is measured and that the pipes work differently than otherwise. And you can perhaps with that not all the literature that exists, but I think that even with flue pipes and dynamics you can do something. It's not a big dynamic range, but I think it's a big gain in expressivity for which it would work. And I think that if you do it with dynamics, with flue pipes, then maybe you end up with literature like for the clavichord with only 2 or 3 voices, because you can't control more than that.
So if you can do this, it would be great, but a control board would be nice.
Yeah. If you could have a swell, that would be nice. But okay.
Hi. So thanks for your talk in the beginning. So a question to microcontrollers and IOs. Have you thought about what would happen if you multiplex the exits, the inputs from the motors? So of course, the step time, there would be a question how it works, but in general you can multiplex that.
Yeah, the direction and end stop, you can multiplex those certainly, but at some point in time you would always arrive at the point where you need more than one, and in the architectural design you probably have to allow for getting it together, and that point alone that you want to separate input and output device, then the MIDI would be enough for that, but okay, the step input I wouldn't like to multiplex, really.
Thanks. We have another question back here. Have you thought about what's the size of the diameter of the valves and how the air is flowing?
You think the rotational valves? We haven't done that yet, but I haven't really done a lot of fine-tuning so far at all with the cross sections for the pipes, for the hoses. That's a factor for organ pipes, really. But I really would couple that to that, seeing what kinds of hoses I can get, which cross sections works with which pipe, and I would just try that with these rotational valves. But I haven't done any calculations yet, so I don't know. But I think it's one of the more charming aspects of the rotational valves, that you can easily build them at different sizes and different thicknesses, and you don't really need 2 magnets for big pipes, things like that.
Oder hast du eine Idee?
Or do you have an idea or suggestion?
So the second thing would be, if you would build a triangle structure, you could have an with round forms, you could have a better reaction time.
Yes, we're not there yet, but we thought about it. Yes, thank you.
Total interessante Vorschläge machen. Wir haben dann auch sehr viele in den Schlangen.
Yeah.
Ich gehe weiter mit Mikrofon 1.
Du hattest schon angesprochen, dass du die Luft...
You already said that you left the air pressure motor back at home, but how do you generate the pressurized air? Because compressors in general are pretty loud. So what kind of construction do you use therefore?
So yes, compressor is quite loud if you want to, especially if you want to have a big one. So for big organs, it's put in the basement and is damped on a damped setup. And if you don't need the huge pipes, even for small organs, I did some experiments, but I didn't bring it along because I don't have a car. So a construction such as in so different bellows small construction, but if you really want to have a serious and stable air supply, that's why the folding bellows was invented, that goes up and down as a whole, which is more complicated than a small bellows. But if you have a bellows that only does it like this, it depends on which angle you have it, and if it has different weights. But these days you know that the bellows knows how much air it is in it, because you have a sensor, and the other bellows that are really pumping, then they change their speed so that so it doesn't go up and down too badly, but keeps at the same level more or less.
From what are they made?
It's also 3D printed stuff. It's the bearings of skateboards, because they are cheap.
Und an dem Fall ist tatsächlich auch der Motor das lauteste.
So in these things, the motor is really the loudest part.
Aber das habe ich noch nicht
But I haven't really tried optimizing that, making the motor quieter. But maybe it's not a stupid idea in a makerspace. It's not a bad idea to make such a construction, such as
aber die Geschwindigkeit der Schöpfbälge anzupassen durch einen Sensor.
the fairground organ, an automatic one, to make a construction like that with 2 pumping bellows and one storage bellows.
Mikrofon 2 bitte.
Okay, so you have controlled the pipes separately. Have you thought about controlling one register with this dynamic? Similar to a synthesizer where you have aftertouch, you could also just control the whole keyboard with one signal. Not that you do this mechanically, but if you have all pipes in one register, open all the waves to register.
Okay, then you get something the same as if you use a swell. You have a dynamic factor that works the same for a whole voice. And I really think it depends on what kind of music you want to play with that. There's something you can use that for, but I really want per key dynamics. But that too is interesting for certain types of music. Yes, of course. Maybe another thing. There's not an evaluation. But some people, I want the key by key dynamics. Others really want dynamics for the whole voice, but you can't play a fugue with that, for example. But there are so many beautiful things on this world.
Noch mit welcher Software ihr diese
Okay, mit welcher Software habt ihr das? Sorry, with this, which software do you make the spectrum of the overtones?
So there was FFmpeg, and the exact command is on the Fahrplan page, on the schedule page, on the of this talk. And if you try that on the terminal, on the command line interface, that should work. Otherwise, you have to ask a nerd how to debug that.
Okay, yeah. One could build an organ at every time arbitrarily difficult, and you had the main point, the controlling. But have you an idea when you would use different register?
I would really like to make an actuator below every pipe. So there's the question, how can you make it cheaper? So no, but we haven't really done that. I'd like to build a prototype so you can at least start playing music, so I can show you what it's about. So 2 octaves and 2 registered, and 1 flute pipes and 1 reed register. And I would make an actuator under every pipe. And if someone is then going to build an organ with multiple registers, then they can of course decide how much money to throw at it. But if I don't really intend to build a huge organ beyond a prototype, among other things because I just don't have the room for it. So is that an answer?
Okay, gut.
Yeah. Okay, thank you.
ja, wahrscheinlich dann auch der Aufruf, dokumentiert eure Orgeln gut, stellt sie irgendwo hin.
Also the call for document what you're doing, make a documentation of what you're doing so that others can build this too and choose from what you're doing to compose it to a new organ. Yes, right. I also have most of the time the same deck number, so at the next event, just call me. So thank you everyone, and thank you for all the questions. And if you build an organ, bring them here to Congress.